In this video, we are going to study the Lookahead transformation. This is a transformation that actually allows us to change the one of the fundamental properties of a signal processing algorithm, namely the iteration period bound. Note that this works only under very specific conditions. What we are going to do over here is to make use of some mathematical properties of the equation that is being implemented and use that in order to restructure the signal processing algorithm itself in such a way that the iteration period bound can be reduced. This is important to keep in mind. In particular, you should not get the impression that somehow the Lookahead transformation is able to reduce or change the iteration period bound of a signal processing algorithm. That is fundamentally not possible unless you have changed the algorithm itself in some way. So let's try and understand exactly how this works. We'll start by taking an example. The example that we are going to consider is a very simple IIR filter. The filter equation is y of n equals a times y of n plus b times x of n, where x is the input and y is the output that's being generated. A fairly straightforward and obvious implementation of this would look something like the following diagram. X of n would be multiplied by b, and the output y of n would go through a single delay element to generate over here y of n minus 1, which would then be multiplied by the coefficient a and added to the x term that we already have. So this structure, in other words, exactly implements the equation that we have here. Y of n equals, beg your pardon, this should be, the equation should be y of n minus a times y of n minus 1 plus b x of n. So this is a fairly straightforward implementation. What we can see over here is a number of things. One is, what is the critical path of this system? Either this path or this. Both of them essentially add up to a total delay of Cp is equal to Tm plus Ta. This determines the clock period that can be used successfully on the system. But in addition to that, the important thing that we need to keep in mind is what is the iteration period bound of this system. That's determined by this loop that we have over here. And the value of the iteration period bound basically turns out to be Tm plus Ta divided by 1, because there is only one delay element on that loop, which in other words is equal to Tm plus Ta. And since we have found that the critical path and the iteration period bound match, essentially it looks as though there is nothing further that we can do to speed up this implementation of the IIR filter. In other words, the minimum sample interval that can be used for processing this IIR filter is in fact determined by Tm plus Ta. This is important to understand clearly. What it says in particular is that even if I try to do some kind of parallelism or unfolding or any other kinds of transformations on this filter, I will not be able to change its fundamental sample period. It's going to always be limited by this Tm plus Ta component that I have. So the question is, what can we do about it? Is there anything that we can do that will allow us to change this iteration period bound? And the short answer is no, you cannot change the iteration period bound. What you can, however, change is the algorithm itself, or in other words, the equation that you are trying to implement. So let's see if there is another cleverer way of writing this equation that allows us to come up with a slightly different implementation, which will allow us to achieve a different sample rate. The modification that we are going to make is to observe that I can substitute the expression for y of n minus 1 in the expression for y of n. In other words, what is y of n minus 1? It's in turn going to be given by a times y of n minus 2 plus b x of n minus 1. So in other words, all that I have done over here is to replace the term y of n minus 1 by its expansion out here. Now let's further simplify this expression. What we get is a square y of n minus 2 plus ab x of n minus 1 plus b x of n. Now, what does the implementation of this look like? The important thing to observe over here is the fact that a squared and ab are both constants, and therefore they can be pre-computed. You do not, in other words, need to do a times a at runtime when you are actually implementing the filter. What you would do is to compute a square as a new number and use that as the coefficient into the filter. So how does this help us? Our new architecture looks something like this, with y of n out here. I would now put it through 2 delays in order to get y of n minus 2, and take that value, multiply it directly by a coefficient a square. I don't multiply it twice by a into a. And now I would need to add it. And what do I add to this? The value x of n into b plus x of n minus 1 into ab. We can see from here that effectively what I have on the left hand side is an FIR type structure, and on the right hand side is an IIR, or a recursive or an infinite impulse response type structure. As far as the iteration period bound is concerned, it's the right side that I'm worried about, because as we know, for feed forward or FIR type structures, I can always apply any amount of parallelism in principle and reduce the iteration period bound arbitrarily close to 0. But what happens on the right hand side? If I try computing the iteration period bound, what I find is that the loop of interest is going to be this one marked over here, which has a total delay of Tm plus Ta, but now has 2 delay elements on it. This is the crucial observation that we have come up with by basically making the mathematical change to the coefficients, which was just based on the fact that we are using one of the properties of multiplication, right? And the fact that the a square coefficient can be pre-computed, we are therefore able to modify the filter. So you should be very clear about that aspect. The original filter that we started with and the new modified filter that we have come up with are in principle different filter structures. In fact, one of the places where this can actually hurt is the fact that when you start using finite precision and fixed point number representation, you will actually find that even the values that are being computed can end up being different in the two cases. However, we are not going to go into those kind of details. We are just going to assume that the number representation is sufficiently precise that we do not run into precision problems and therefore other stability issues with regard to the implementation. What we do on the other hand have is the fact that by modifying the filter in this way, we can reduce the iteration period bound. So the question of course is this an actual improvement, or is it just something that we have observed in terms of the structure of the filter? Can we actually make use of this in order to get a better implementation? And in order to actually speed things up, what we need to see is, can we now use this modified filter structure and obtain some kind of a parallel implementation of the IIR filter? So to understand exactly what we mean by a parallel IIR filter, it makes sense to go back and look at the original filter that we started with, which was without doing the Lookahead transformation. What we have is just something like this: x of n, b, y of n, coefficient a, and the two values are added together. The data flow graph corresponding to this, I'm going to leave out the part of the x of n because it's the FIR structure. I'll concentrate only on the IIR or the recursive portion of the graph for now. What it effectively looks like is something like this. I have a multiplication which in turn feeds into an addition and comes back with a single delay. This means that the iteration period bound over here is going to be given by Tm plus Ta divided by 1. The critical path is also given by that, and so on. Right? What happens if we tried implementing a parallel version of this? The way that we would do that would essentially be by saying, let's unfold this graph, a two parallel unfolding. What the structure that we would end up with would look something like this. X0 would feed into plus 0. The output of plus 0 is to be used by x1 directly, and therefore what we find is that we have a direct edge from plus 0 to x1, then an edge from x1 to plus 1, and finally an edge going back here with a single delay, because this essentially corresponds to the path which is leading from plus 1 to x2, which in turn is a delayed version of x0. Now what does this mean? The resulting graph that we have over here has an iteration period bound of 2 times Tm plus Ta divided by 1, which basically means that the sample interval, the best sample interval that we can get, is equal to 2 into Tm plus Ta divided by the parallel factor, which is equal to Tm plus Ta. In other words, trying to parallelize this basic IIR filter is of no use whatsoever. It does not help us to improve our sampling rate at all. Now what happens if I take the Lookahead modified IIR filter? The structure of the Lookahead modified IIR filter is something like this. I have 2 delay elements and of course the initial part which corresponds to the x, that is b, ab and a squared. Once again, for simplicity, I am going to concentrate only on the recursive portion. What we have is the multiplication feeding into an addition and a feedback loop with 2 delay elements on it. Now what happens with this? What we find is that the iteration period bound in this case is actually equal to Tm plus Ta divided by 2. But as it stands, the critical path is still equal to Tm plus Ta, which means that I now have a problem, which is that the sample interval is going to be equal to Tm plus Ta. As before, there are 2 things we can do over here. One is, if the multiplier and the adder have more or less equal delays, then we could just use a pipelining transformation over here. And yes, this is perfectly legitimate and would work fine to reduce the time taken inside the filter, or in other words, to increase the throughput of the filter. The other alternative that I could do would actually be to do an unfolding transformation once again. And when I unfold this new graph, what I find is I have x0 feeding into plus 0. The output of plus 0 is going to be used by x2, which is the 2 delayed version, which is basically a 1 delayed version of x0. Similarly, x1 feeds into plus 1, and its output is going to be used by x3, which is a 1 delayed version of x1. So effectively what I have over here, in other words, is there are 2 graphs, each of which, when I combine the entire system together, I find that the iteration period bound is equal to Tm plus Ta, which means that now the sample interval that I can get on average is equal to Tm plus Ta divided by 2, which is the parallel factor. In other words, this modified or Lookahead modified IIR filter is able to get a sample interval which is half that of the original IIR filter. Or to put that in other terms, it can process samples at double the rate of the original IIR filter. So we can see that the Lookahead transformation has actually resulted in improving the rate at which we can process samples using the IIR filter. Now let's see if we can take this idea further. What we would like to do is there a more generic way by which I can obtain the transformed filter rather than by just writing out these equations in detail? And it turns out by looking at the frequency domain, it makes it a little bit easier for us to understand how exactly we can derive the lookahead versions of different IIR filters. So as an example, let's consider how we could have derived the lookahead version for the simple first order IIR filter. For that, what I'm going to do is first write down the transfer function of the IIR filter, which is h of z as 1 over 1 minus a z inverse. Now keep in mind that this is assuming that the coefficient of x, that is what was written earlier as b, is just equal to 1 for simplicity. Now effectively 1 over 1 minus a z inverse translates into exactly the kind of filter structure that we have originally. What you can see over here, this essentially corresponds to the equation h of z, or to rewrite it, essentially what this would correspond to is y of z pi x of z equals 1 over 1 minus a z inverse, which is essentially yz is equal to a z inverse yz plus xz, which essentially is exactly the same structure that we had implemented earlier, except for the fact that the coefficient of b is set equal to 1. Alright, so now with this transfer function, what we can do is a simple mathematical manipulation. We will multiply and divide by this term 1 plus a z inverse. What does that give us? Basically what it says is h of z is now equal to 1 plus a z inverse divided by the original term 1 minus a z inverse into 1 plus a z inverse, which if we expand it out comes out to be 1 plus a z inverse by 1 minus a square z power minus 2. When you go back and look at the original structure that we had derived a short while earlier by expanding out the y of n minus 1 in terms of y of n minus 2, you will find that this is exactly the same expression. It's just that we have derived it in a different way. The advantage of using this technique is that now it suddenly makes it a lot easier to understand how we could do this one step further. I could also have written h of z as 1 plus a z inverse plus a square z power minus 2, and by expanding out that term in the denominator, I will find that I get 1 plus a z inverse plus a square z power minus 2 by 1 minus a cubed z to the minus 3. In other words, deriving the corresponding expression and structure for a much more advanced form of the lookahead transformation becomes easy when we understand that we can also look at it in the frequency domain and use the mathematical manipulation directly there. Now what happens with higher order filters? Let's consider the case where h of z equals 1 over 1 plus a, or 1 minus a z inverse plus b z to the minus 2. You don't need to worry too much about the plus or minus signs. They can always be handled separately. This is just for convenience in terms of the expression that I was writing earlier. Now what I would like to do in lookahead is make sure that the loop with the minimum number of delay elements on it is the one that is eliminated, or I'm able to somehow insert extra additional delays on it. In other words, my problem over here is because of the z power minus 1 term. If my first non-zero term was z power minus 2, then it would mean at least 2 delay elements in the feedback loop. which would allow me to do some form of parallel transformation or pipelining. So if I just take my goal as how do I insert an additional, or how do I get rid of the z power minus 1 term in the denominator, then the idea becomes relatively simple. I can basically go about doing it by this. Once again, multiply and divide by 1 plus a z inverse, and the result is going to be 1 plus a z inverse by, I'm going to write out the expression over here, 1 plus a z inverse minus a z inverse minus a square z power minus 2 plus b z power minus 2 plus ab z power minus 3. These two terms cancel out, and the rest reduces to 1 plus a z inverse by 1 plus b minus a square z power minus 2 plus ab z power minus 3. Now this makes it very clear that we have managed to basically eliminate the z power minus 1 term from the denominator, and as a result we effectively have a structure which in the denominator would look something like, the data flow graph for it would look something like this. Of course, this data flow graph has been intentionally drawn in this way, assuming that you just want to capture the effect of the delays. It helps to make it very clear that there are two loops involved over here, and each of those loops in turn has a different value for the iteration period bound, and that you could then calculate the value as the IPB for this one would be equal to Tm plus Ta by 2, and for the outer loop would be Tm plus Ta by 3, and therefore the maximum would be determined by, the larger value would be Tm plus Ta by 2, which in turn is going to be the iteration period bound of the overall system. Now if you implement it in a slightly different way in terms of how the additions and multiplications are combined or placed one after the other, you might end up with a slightly different value for the iteration period bound, but that's just a question of how exactly you are ordering the different additions and multiplications. Once again, that's not really changing the algorithm in any significant way. The Lookahead transformation is the one that has made a significant change to the algorithm as such. So the purpose of this was basically to show that there are certain kinds of situations in which we can actually make fundamental changes to the structure of the architecture that we get for a signal processing algorithm. The property of iteration period bound that was derived is actually something quite fundamental and is not to be taken lightly. It actually does set fundamental limits on the best sample period or the sample interval that can be used for the system. Changing that is not possible through the regular manipulations or transformations. Pipelining, parallelism, all of those always respect the iteration period bound and do not try to change it as such. On the other hand, what we can see is that if we have further domain knowledge, in other words, when we know that we are actually doing mathematical multiplications and additions, as in the case of the IIR filter, we can use certain properties of those particular mathematical operations, effectively use them in order to change the algorithm that is being implemented, and the resulting algorithm in certain cases, if we have done it right, can have a lower iteration period bound and therefore a lower sample interval than the original structure that we started with. This is not restricted only to IIR filters. One of the places where it has found significant use is the Viterbi algorithm, where it turns out that there is a similar kind of a loop. There is a loop in the structure where you need to add a certain metric value, compare it against the previous metric, and then decide which one is the survivor. Once again, it looks very similar to an IIR type of filter. The operations are not directly multiplication and addition. In this case, they are addition and comparison. But it turns out that because the addition and comparison follow the same kind of mathematical properties, we are still able to do a look ahead, and a similar kind of reduction in the critical path or the iteration sample period can be obtained in such a case. There are other places as well where this can be done, but keep in mind that it can only be done when by exploiting some property such as the underlying mathematics of the system.